Welcome to the weekly ITS Davis seminar. Today, we're delighted to have Professor Srinivas Peeta as our speaker. And Professor Peeta is the Frederick Dickerson Chair and Professor in the School of Civil and Environmental Engineering and School of Industrial and System Engineering at Georgia Tech. He's also Principal Research Faculty at the Georgia Tech Research Institute. So before moving to Georgia Tech, Professor Peeta was the Jack and Key Hokima Professor at Purdue University and was the director of the Nexus Center, which is the US DOT Regional University Transportation Center for Region 5. And he also served as the Associate Director of US DOT Center for Connected and Automated Transportation. So Professor Peeta received his Bachelor of Technology, master's degree and PhD degrees from Indian Institute of Technology, Madras, Caltech, and the University of Texas, Austin, respectively. Professor Peeta's interests are quite broad and generally spans transportation and infrastructure systems. So today, we are very pleased to have Professor Peeta to give us a talk on his most recent research. Srinivas, and the floor is yours.
Thank you, Michael, and thank you for having me in the seminar at UC Davis. I just wanted to start out with a piece of trivia. Exactly 2 years ago, I was at UC Davis to attend a autonomous vehicle experts group workshop. So that was physically. And today I'm very happy to be there virtually. And that's the sign of our times. Okay, with that, I'll go ahead with to the next slide. In terms of the problem that I'll be talking about today, and that's related to how we look for strategies to deploy routing in real time using incentive mechanisms that leverage connected and autonomous transportation technologies. For travelers, routing or route determination is a key decision as part of their travel from their origin to their destination. And over the past 3 decades or so, dynamic traffic assignment has been identified as the engine to determine routes in real time, which address the performance from a system perspective. That means to optimize some characteristics at the system level, or to describe what the system looks like, while meeting certain individual constraints or behavioral characteristics or objectives. And over the past couple of decades, a lot of focus has been in terms of enhancing the realism and accuracy of dynamic traffic assignment models. However, there are challenges to deployment even today. The first point to note here is people are different. So the drivers in a traffic network who are going from their origins to their destinations have varying characteristics, attitudes, and behaviors. And most of the dynamic traffic assignment models seek to use user classes to capture elements of this heterogeneity. However, even with the use of user classes, it tends to mask the variations at the individual level. So in reality, or ideally, if we can get to that level of the individual, and these days that may be possible depending on the type of technology that we're looking at. So if you have the ability to track mobile devices or have apps in them, that provides a possibility. The other aspect related to this is that even if you're able to come up with user classes in terms of behavior or user heterogeneity, to track their fractions in the traffic stream in real time can be rather difficult. What that means is we don't know what percentage of drivers belong to which group, and that can change with time. And as we note here, when we say dynamic, we are looking at conditions or traffic conditions that are changing with time, which means we are seeking to find routes under dynamics as well as sources of randomness that show up. And one of those sources here is the randomness in the fraction of user classes. So that leads to difficulty in terms of prediction for short-term or operational reasons. So when you're looking for traffic operations and we're looking for predictions in the short term, there may be challenges there. On the other hand, if we want to use this from for a planning perspective, where we're trying to come up with solutions where the variations within may not matter as much because we are looking at solutions related to investing in resources, for example, adding new lanes, new roads to improve congestion in a certain area. So those are the kinds of problems where some of this could be more relevant. The other aspect, and in today's world, when we talk about information availability in dynamic traffic assignment models, in many models, there has been an underlying assumption that we have sensor data on all links. And even with what we have today, that can be rather optimistic in terms of the technology related to sensor coverage. So in reality, we may not have such sensors available on all links of a network, because if we are trying to come up with accurate predictions, we need to have information at that level that allows us to come up with meaningful solutions. The other element related to this is that even if such information were available, there is this notion that that is seamlessly available to all travelers in real time. And that is challenging as well, because different drivers may have different levels of access to technology. And beyond that, even if they did have technology that allowed them to get information in real time, in an inherently complex multitasking environment that we have when we have congestion, we can have distraction and the ability challenges related to cognition, where the load that this brings up can be challenged. The last aspect related to the deployment, which is particularly challenging, is the computational tractability aspect. So even if you look at where we are today, analytical solutions or analytical approaches to solving these problems, the dynamic traffic assignment problem, they lack modeling realism. And even if there are models that are out there, they'll have limitations that preclude their application in general context. The other aspect related to that is that the computational time can increase rapidly as the network size increases. And that's why simulation-based algorithms, where simulation is used to capture the dynamics of the traffic flow, have been used to come up with deployable solutions to the dynamic traffic assignment problem. However, in a computational context, a centralized approach, which implies, for example, we are trying to solve, say, for the best performance of the entire network. Say, we are looking for the Atlanta region. Then the computational burden can be significant. And even here, there are some levels of computational adjustments that are made, because there's the use of mesoscopic traffic simulators, where the individual vehicles can be tracked from a behavioral standpoint related to routing, but the movement of vehicles is done using macroscopic traffic flow relationships, primarily to reduce the computational burden. So all of these already exist, but even with that, when we look to reasonably sized urban network, coming up with the solutions in real time can be particularly challenging. And there are different approaches people have used to try to adjust them and so on, but nevertheless, there are challenges. So in this context, if we have emerging connected and autonomous technologies, there is the ability to use vehicle-to-vehicle communications and vehicle infrastructure communications in a local area to obtain information with a reasonably high level of fidelity. So that is something that can be leveraged. The other aspect is, if we look at solutions which focus on the local area because we are looking at local information that's available at a certain level of confidence. Then we can use decentralized computational approaches. And finally, if we can focus at the level of individual preferences, which means rather than grouping them into user classes and then masking variations at the individual level, if we can get to the individual level itself, that can be particularly attractive. And while most solutions related to mitigating congestion, many solutions are focused on supply side approaches. Many of them tend to be rather expensive because they involve building a new road, building new lanes, and the other side is demand side solutions. And demand side solutions have existed to manage congestion for quite some time. Even if you look at it in the 80s, where they looked at peak spreading, where the peak period demand is spread for a longer period of time by proposing incentives, and some of those can be at the level of a company where they provide tax incentives and so on. But even if you look at incentives that people have been suggesting in recent years, they require monetary investment from some stakeholder or group of stakeholders. So that can be particularly problematic if that requires a new dedicated revenue source. So what I mean by that is there is some budget line that needs to be provided for that. And typically, these tend to also target groups of subpopulations or certain types of populations, with the idea that then these are passive approaches in the sense that they try it out, there'll be some subset of people that respond to them, and then they see how much benefit is obtained in that sense. So to a certain extent, it has definite intelligence in them because they're targeting aspects of human attitudes or behaviors that are rational, but also in certain way they can be throwing a dart because they're passive in the sense that they target and then see what is the effect. So in some ways they are reactive. And many of them tend to focus on macro travel decisions. And what I mean by macro here is in terms of shifting the travel mode or the time they're departing. And many of these are primarily because of potential safety concerns if you try to deploy them in real-time context, because you have distraction, as I mentioned earlier, cognitive burden, and then when you have multitasking, the driver has limited attention span in terms of trying to leverage that. The other aspect related to these mechanisms, there are certain assumptions in terms of obligations. The first is that there is an assumption that a subgroup or everyone will participate, and that need not be true. Because that actually goes back to what I mentioned earlier, which is trying out some of these mechanisms and seeing which subgroup or group responds to it. The other aspect here, which also is particularly important, is behavior honesty. And what that means is it assumes that the people would follow the design rules with a certain level of obligation and without any intention of gaming the system. And that typically is contrary to human behavior. If they can game, people do that because their individual objectives are what matter to them rather than some social or system level objectives. So we seek to focus on incentive-based routing strategies which first leverage the CAV environment, where, as I mentioned earlier, connectivity allows us to come up with local information with a reasonable level of confidence or fidelity in terms of their relevance and accuracy. The use of automated en route decision making for safety. So what that means is the autonomous vehicle, and that relates to the next one, where we say use deterministic choice behavior in terms of ability maximization, where the underlying assumption is that people would put in their preferences, and these preferences are transparent. What that means is, if I look at it from the perspective of human-driven vehicles, then as an analyst, someone who is looking at the situation from afar, I may not know the actual factors that affect individual decision making, or some of them are latent, right? So this is where having a CAV environment where there is this automated ability and where we have these preferences coded in transparently, there is the ability to leverage that aspect. And then these incentives can be focused at the level of the individuals, because we can characterize their utilities. And from that, we can link the incentives at the level that we capture the heterogeneity while we are making it consistent with their attitudes and behavior. Now, the other element I want to mention here is that we allow negative incentives. And what I mean by that here is there'll be some users in the system that will pay, and there'll be others that will benefit. Primarily, when it's the benefit, I have to be careful. Some users will pay to gain in terms of travel time. Other users will receive monetary benefits because they sacrifice. And this is where we talk about budget balance, in the sense that we can make it cost neutral if that is one of the underlying constraints in implementing this in the real world. I mean, there may be situations where transportation agencies would be very willing to provide that budget line, but at the conservative level, we wanted to start off with a budget balance. And there's a assumption here that CAVs will have a positive expected utility if they have a positive expected utility that is sufficient for them to participate, or the willingness to participate. And what I mean by that is, if I look at it over a period of time, say a month, then sometimes they may have actual negative utilities, whereas most of the time they actually have positive utilities. So their expected utility is something that allows them to participate because they see benefits for themselves. And in terms of the behavioral properties, we note that there is this notion of envy freeness, and that implies that individuals are satisfied the most with the routes and incentives that are assigned to them. What that means is, if I change the route or the incentive, their utility will actually go down. Another aspect here is their willingness to participate. That's guaranteed through the incentive design. And we don't require a behavioral honesty assumption in this step. That is obtained primarily through the design of the incentive itself. And we actually prove all of this analytically. What that means is, if I try to cheat, then I actually will have negative additional utility that is incurred. So in this context, if I'm talking about incentives, the incentives that are being provided will satisfy behavioral properties in such a way that it does not require us to make assumptions that can be limiting in the real world. And finally, I already mentioned decentralized computing. So in terms of the framework that's there, we have periods tau minus 1 tau. So these are just periods of interest in which we deploy these incentives. So we start out with route flow assignment. So we try to identify routes that determine some optimal routes, and I'll talk about that. And once we have these optimal routes, we assign vehicles to those routes. And we'll talk about it later that there's no requirement that they have to accept the routes that are provided willingly. So it's the incentive mechanism where we fine tune all of that. So we have the optimal route assignment, and then we have the incentive mechanism that determines the optimal incentives, and these are then deployed in that context. So we start out with the first one, and I already mentioned this previously, that if you look at the figure there and the encircled area in green, what it is telling is, even though my objective is to travel from R to S, my information is obtained from V2V communications with a high level of fidelity, which is more recent information that I can use only for a local range. And within that local range, I now determine what is my best route to satisfy the objectives. In this case, we come up with what's called an approximated local system optimal solution. And I'll tell why it's called an approximated one. Primarily, it is related to the fact that the rest of the routing that you see from omega and kappa to S, they're shown in dots. And all that implies is the information that we have in terms of the traffic conditions for that part may be dated. So we anyway don't have a high level of accuracy in terms of that data. So rather than look for system optimal solution, we seek to equalize the marginal travel costs, right? So what we look for here is that the differences in marginal travel costs will meet some tolerance level rather than satisfy it precisely. Then we have a route flow assignment context here where the information availability assumption is realistic. And then the other point is, because we're using a decentralized approach, it also scales well the dynamical system. And here we use the dynamical system conceptually. It is similar to what Mike Smith uses in the context of day-to-day switches of routes. So conceptually it's the same, but it is of course adapted in the context of the routing in real-time context. Then we assign the vehicles to routes to achieve these optimal route flows, but in such a way that the sum of their utilities is maximized. And we'll see later that this can be solved as a linear program because that again has computational benefits. And finally, as I mentioned earlier, the compensation procedure that is developed will neutralize any user envy that is there of other route options, okay, as well as ensure that we have individual rationality and individual incentive compatibility using individual utility maximization. And the point that I was mentioning earlier is the advantages of doing this. For the first objective route flow assignment, we don't need to factor the incentive budget at this point. And that's all addressed in the incentive mechanism design. We solve a single objective, a convex optimization problem in this context. The same thing, even when we assign objective, when you look at objective 2, assignment of the vehicles is done without consideration of whether these vehicles will accept the results or whether they'll game the system. And again, this is addressed, as I mentioned earlier, in the incentive mechanism design, where we preclude this gaming and will ensure that the best they will get is, in terms of utility, is the one that is assigned to them. That's why these are optimal incentives, and the assigned routes are the optimal ones for them. And the incentive mechanism satisfies the budget balance and the behavioral properties I mentioned earlier. And if you look at this slide, you'll note that we have a model. So we look at the second column here. So we have the route flow assignment, vehicle route assignment, and then the incentive mechanism. And each of them have outputs that we discussed before. Finally, we have the optimal incentives in the first column. And if you go to the third column, that illustrates the methodology that's used for the route flow assignment. We use a dynamical system. And in the vehicle route assignment, we use maximizing the group utility. And then we develop NV-free methodology for incentive mechanism. And you'll note that in each of those, there are properties that we can illustrate analytically. So for the first one, we show flow conservation, non-negativity, and convergence, because these are required in the real world. Then we'll note that when we are doing the vehicle route assignment, we'll link to the budget balance, because there is the issue of who pays, who doesn't pay, that will link to that level. Whereas the NV freeness comes with ensuring the budget balance, the individual rationality we talked about, and the incentive compatibility as well. So if you look at the first one, which is the route flow assignment now, we can go into a little more detail. I won't be looking at the mathematics. I'm just going to illustrate the underlying essence of what that map shows, because we don't have sufficient time here, okay? And if people are interested, there is a paper out associated with this, which has the details of the mathematics associated with this, okay? So the output of the route flow assignment are the optimal route flows from, for example, here from R to S, but we are looking at R to omega, R to kappa, and so on, where the strategy has the time horizon divided into small time intervals, as I showed in the original hierarchical framework. And we have the real-time traffic information that is done, updating that is done only for the local area that's shown in the green. And we do the local route assignment. Okay, and in the process, we want to be clear that even though globally what we have may be an approximate one because we don't have accurate information on traffic conditions for the dashed lines, which means the rest of the network. So in that sense, what we do is we come up with a approximate local or approximated local system optimum also solution. And this is where, if you look at what we say, the delta there says global marginal cost difference tolerance, whatever tolerance limit we have. So that tolerance is a reflection of the fact that outside of the local area, there is some uncertainty in the information that's out. So that's why it's an approximated rather than a precise or exact system optimal solution. And the route switching, as I mentioned, is based on Smith's day-to-days in a similar way. So it's proportional to the path cost difference between routes. And so the overall switching rate for any path flow has two components. So we have flows switching to this path from other path because basic benefit, and all traffic flow that is switching out from this path to others. So if you see the net of it, when we add some and we subtract some, that would be the overall switching rate for path flow I. And then we look at the flow conservation and non-negativity. And so here, what I'll just mention here is we illustrate analytically that the flows are non-negative, the feasible flows, which means if they satisfy the constraint set, the feasible flows are non-negative, and also that our demand constraints hold for feasible flows. And what that means is they ensure the flow conservation. And in terms of convergence, I'm just showing the final theorem that's there. But essentially what it means is if we start from any feasible path flow solution, the proposed dynamical system, actually should be dynamical, I apologize, should always converges to the also state, which means the approximated local system optimal solution. And then we go to the next one, which is the vehicle route assignment. And in the vehicle route assignment, we assign vehicles to the local routes so that we maximize the sum of their individual utilities. So here we see the vehicle set. And the point that I want to emphasize here is that when we talk about the individual utilities, there is a route evaluation function that's associated with the newly assigned route and the initial route. So what are the trade-offs between them, which is the difference between the two of them? When I say vi eta I and vi mu, that tells us what are the differences in terms of that route evaluation function. And then there's a payment that is associated with, depending on whether somebody benefits or not, we have a positive or negative value. So the utility for the individual is determined by the route evaluation function, and the P, as I mentioned, is also linked to the budget balance. That is, how much is the payment, who pays what, and so on. And those are determined as part of the incentive mechanism. So this is why we say we have budget balance, because across all users, we'll see that the sum of these payments will be zero. And what that means is this is a zero-sum game. Some gain, others lose. But and what that means is I have to be careful when I say some gain, others lose. It's simply in terms of the monetary side. Some pay, others benefit monetarily. That doesn't imply that their utilities are negative or positive in that sense. That depends on their gains related to their travel times and so on. So here, what you'll note is when you look at the objective function, that's exactly mentioning that, the individual utilities. So if you look at that function there, it has a component B, which the objective function, which says it takes a value 1 if vehicle I takes route rho, or it has a 0 value, which is what makes it a 0-1 integer programming problem. But the other element to note here is that there is the property of total unimodularity that can be leveraged related to the constraint matrix. So there is a theorem which says that if the constraint matrix has total modularity property, and then we have integer variables, then we can solve for the LP relaxation, which means we can solve for a linear program, and the solution of the linear program will turn out to be the solution for the integer program as well. And that's because we are leveraging the property of total unimodularity. And this is where that simplifies the computation. And again, it's linked to the computational tractability that we are talking about. The incentive mechanism is the following. Once we have the vehicle route assignments, which are the optimal ones, which means related to ensuring the also state, then we seek to design cost-neutral incentives that the users are satisfied with in terms of the routes, and also they behave honestly. And now we'll talk about what we mean by some of those. So first is the NB freeness. And if you look at the utility here, the utility function U, the utility obtained by any user or agent or driver by selecting another route will not be higher than that of the one assigned to him or her. So what it's saying is, what we determine through the incentive mechanism and the route process, optimal routes related to ensuring the approximated local system optimal solution will be the one which has the most utility in that sense. So we cannot count with anything that has better utility than that. And in terms of individual rationality, if we can illustrate that these vehicles, the connected autonomous vehicles, are at least as good in terms of performance from their utility point of view by participating as opposed to not participating, then that automatically provides that incentive for them to participate. And finally, budget balance. In this case, we are saying we are collecting money from groups of vehicles whose average travel time decreases. So they are benefiting, and we are paying vehicles whose average travel time increases because they are sacrificed. So this is how we do this. And in terms of the last one, the incentive compatibility, so that links to the behaves honestly part. So how do we do that? So the utilities that agents can obtain by reporting the true evaluation functions. In some sense, what we look at here is their value of time. If they try to gain their value of time and fake it versus stating the true value of time, we'll show that they actually lose out. So in that sense, the utilities are higher when they use their true route evaluation functions rather than any gamed up version or a fake one. And that actually promotes honesty naturally. So that's again one of the aspects related to the incentive mechanism. And then if you look at the incentive mechanism, there is a compensation approach that was a procedure that was proposed by Harkey et al., which eliminates the NV of initial assignment. What that means is, if initial routes are randomly assigned, they can be, in some ways, some people can benefit, others can, may lose out, versus routes that are actually determined based on the need to reach the approximated local system optimal state. So if there is any advantage that a random initial routing generates, that can be taken out by having these adjustment incentives. And there's a procedure that allows us to guarantee that we can reach NB freeness in n steps, which means we can determine these adjustment incentives for different users. And I'll actually go into a little more detail slightly later on. And what we'll notice that to ensure fairness, the incentives will be paid by all agents once they're determined. And then we'll see the adjustments, which will lead to some people having a net amount where they receive money and others who don't. And the incentives are related here to the current route. So agents that have better initial routes, that have better initial paths, would envy agents with worse initial paths. And that may seem counterintuitive. When you say better initial paths, what that means is they have better travel times. So why would they envy agents with worse initial paths? Because the agents with worse initial paths may receive higher compensation. So to take out the unfairness related to the randomness of the initial path assignment, what we do is we come up with an approach that allows us to have envy-freeness in an expected sense, where, as I mentioned earlier, we can guarantee that in a certain number of steps. So there is a procedure that we can identify for this, where we come up with the expected envy-free compensation procedure. And then what we have is we have properties associated with a budget balance and individual rationality. So what I want to take the takeaway message from this slide, where we prove these, is that vehicles are willing to participate only if they believe that the new route options that they have are better than after the flow adjustment on average, which means if they lose out always, there is no real incentive for them to participate willingly. So the willingness to participate will make sense only if, in an expected sense, they are having better options over time. So if one day they lose out, and many other days they gain, that would be the basis for them to participate willingly. And so what we have here are the steps associated with trying to get past that compensation that we have to get past that envy related one, which comes from the initial random assignment of the routes. So after that is done, the next step is we ensure that this condition in terms of expected envy-freeness is satisfied. And in terms of the budget balance, as we said, or the sum across all payments will be 0, which means when we have the optimal vehicle assignments, they do not change if we do the following. And if there is a system operator who can profit from, when I say profit, all that means is they can gain revenue from vehicles that benefit and use that to compensate those that are sacrificing, do it in such a way that for each individual, the rational solution based on their individual utilities. So if the path cost functions represent the marginal cost, so since we are talking about the approximate local system optimal solution, when we say in that context, then the approximate equilibrium becomes the approximate system optimal state. And in the process, because we have better solution in terms of optimizing the performance, the average travel can be reduced. And in the long run, we can achieve a budget balance by adjusting a term related to that. And finally, we have incentive compatibility. And in terms of the incentive compatibility, by revealing their real evaluation functions, CAVs will have utilities as good as, if not better, than if they use a game one, or if they're not being particularly fruitful. And the incentive compatibility related to this is not particularly compatible with envy-freeness and budget balance constraint. What that means is it acts contrary to that, so their objectives can go against each other. So in order to ensure that we have the ability for satisfying incentive compatibility with envy-freeness and budget balance, we propose an expected incentive compatibility, which means that the users or agents or drivers will not have better utilities by manipulating their reported preferences in an expected sense. Again, what that means is when we do it over a period of time, that in an expected sense, they're actually gaining. What that means is any individual context, they may, on a particular day, they may lose out, but when they look at it over a period of time, they'll be gaining. And we also show that for a particular form of that, which is simply, in this case, we use lambda, where lambda is value of time and t is the travel time associated with that particular route. We show that if that evaluation form function has that form, and where we have a uniform distribution from the lower end of the value of time to the higher end of the value of time, then you cannot manipulate the value of time. So you cannot say that your value of time is higher than what it is in gain or lower than what it is in gain. And that's what we illustrate here by calculating the expected utility under different scenarios. So there are 3 scenarios where we say lambda g and lambda f in the bottom, where it says lambda g and lambda f. Lambda g is the what we call genuine value of time for that individual, and lambda f is a fake one. So we have to look at all scenarios to prove that there is expected incentive compatibility. If the genuine one and the fake one are the same, so what that means, they're being truthful, then there is no trivial case to illustrate. And then we also show that if the fake value of time is less than the real one, their actual one, even then they actually lose out, which means they have non-positive additional expected utility, which means they have either 0 or less than that. So they actually lose out in terms of their expected utility because it goes down. The same thing can also be illustrated when they state that their value of time is higher than their actual value of time. We can again show the same thing. The only condition that needs to be satisfied there, and you'll see that in most situations, this is true. There are only conditions when the following happens that we have an issue, and that is if they can gain positive expected additional utility only if their fake value of time is greater than the lambda g, which is their actual one, but less than lambda g plus a particular term, then 2 divided by n, and times the lambda upper bound minus the lambda lower bound. And what we do here is we then look at the lambda, the scale of the lower bound and upper bound in terms of the value of time, and we break it down into units, where if we have the unit as delta lambda, if that unit contains this 2 divided by n, where n is the number of vehicles actually, lambda u minus lambda l, then what will happen is when we have lambda g, the next one will be a value higher than lambda g plus 2 divided by n times this. So what I'm saying here is that value will be somewhere in between, but when we measure either this or the next one. So in that sense, we can get past the situation where there can be a positive expected additional utility. So we can, in the real world, come up with a unit such that that unit contains this value, this term here, 2 by n lambda u minus lambda l. And we actually have an example in the paper to illustrate how that's, and it's completely fine because n tends to be a large number in the real world because it's the number of vehicles, and lambda u and lambda l tend to be within a range, but the order of magnitude is much smaller than the number of vehicles. And then we know numerical studies. What I want to show here is if you look at the convergence criterion, you'll see that it performs pretty well in terms of the convergence. So it can converge rapidly to good levels of accuracy. But the one I really want to illustrate here is what I said related to the expected incentive compatibility. And that is when we plot the additional utility. So if you plot the expected additional utility that agent with the actual value of time lambda g gains by reporting a fake one lambda f, you'll note the following. The highest additional utility will take a value 0, and that is when lambda g is equal to lambda f. What that means is the two of them, the individual is being honest. anywhere the individual is not being honest on either side, you'll see that the expected additional utility has negative values. So it's actually going minus 0.5, minus 1, minus 2, and so on. So the individual loses out unless he or she reports their actual or genuine value of time. And that will promote honesty in terms of this mechanism rather than their ability to game the system. So in conclusion, we come up with a deployable approach that leverages connected and autonomous vehicle technologies, where we use CAVs to illustrate this incentive mechanism and how that incentive mechanism can be used to come up with computationally tractable approaches, where we also simultaneously can account for individual characteristics in terms of their behavior by using a carefully designed incentive mechanism. And we can solve it analytically and implement it in a fully decentralized way to address the computational burden. And the incentive mechanism has some desirable behavioral properties which reinforce its ability to be used in the real world without having to worry about participation on honesty, behavioral honesty, and so on. So in that sense, given that we are assuming that this is a connected and autonomous vehicle environment, we wanted to open a new direction related to how incentive pricing strategy or pricing strategies can be used to leverage these new technologies. In terms of future directions, we are looking at incentive-based platoon decision strategies because we want to leverage the notion that when we have connected autonomous vehicles, there's going to be a lot of platooning that's going to go. The other point here is these strategies that we illustrated with the assumption that our environment is a connected autonomous vehicle environment. The question that naturally arises is what happens when we have human-driven vehicles. In that context, we leverage edge computing in mobile applications because we can maintain privacy. We now use random utility maximization because as analysts, our ability to observe the behavioral characteristics is not complete. So there are latent characteristics out there that are difficult. And also, when you have humans doing the driving, then non-negative incentives may not be acceptable to people. Because if I'm going to pay, so would that be something that I'm willing to do? So that's another aspect that we are looking at currently, where the objectives then become coupled because we can look at traffic system performance and incentive costs simultaneously, as opposed to doing it sequentially when we have the connected autonomous vehicle environment. And finally, once we do that, our objective is to address what is going to happen in the near future when we are going to transition from fully human-driven vehicle environments to connected autonomous vehicle environments, where we have mixed traffic flows of human-driven vehicles and connected autonomous vehicles. And these are some of the references that are quoted in the presentation itself. And I want to acknowledge my PhD student advisee, Chaoji Wang, whose work this is based on. And there's a citation for this, which is a paper that's been just accepted for publication in Transportation Research Part B. And it also was accepted for a podium presentation in ISTTT Beijing, which is supposed to be conducted this year, but it has been postponed to next year in light of COVID-19. With that, if there are any questions, that you have afterwards, please feel free to ping me at my email address. And thank you.
Thank you, Srini. So now we come to our question and answer session. But before we open up to questions, I would like to have Professor Peeta share with us his perspective experience as a faculty. He's been very successful in his career, and some of our graduate students aspire to become faculties. So it would be very nice if you can share your insights and some advice to our students.
So I will briefly start. I did my undergraduate bachelor's degree at Indian Institute of Technology, Madras in India. And then I went to Caltech, and they don't have a transportation program. But I got interested in looking at analytical problems where I wanted to use operations research techniques. And just as a anecdote here, then one of my friends who was working in that area, he said, there's an up-and-coming professor called Hani Mamasani, who's at the University of Texas, Austin, who's doing work in this space. Maybe you'll have interest. So I wrote a 3-page handwritten letter and thought, let me send it out, see what the worst thing that will happen. And I don't think I've shared this before, but he responded with a 3.5-page typed letter. And that told me my choice was completely, the right one. And he so because I told why I wanted to switch, because I was switching from Caltech to another school. So I was telling him why I wanted to go to transportation and so on. And then I was at the University of Texas, Austin. I did my PhD with Hani Mamasani. And I've never regretted that decision. And the reason for that, as all know, transportation is an inherently multidisciplinary field. And today, what you are facing, the world you will be facing going forward, will make it especially so because you're looking at what would otherwise previously be considered non-traditional fields. They are interacting and intersecting with what we do in transportation. And this has always been true, except that now it has been magnified, the challenges that we see with technologies that are very different from technologies that have existed for the previous, say, 100 years, where, as I said, the human will cede control to an autonomous system at some point. So with that as a starting point, there's another thing that I wanted to mention. So I was fortunate to receive, so one of the things I have to tell is, as a student, you have limited time that you have where you're doing your master's or PhD, and you want to aspire for the best you can. What I mean by that is you want to excel and gain as much knowledge and do the best you can in terms of aspiring to address new problems. Anytime we address new problems, that tends to have high impact on the field because these are problems that the field is facing challenges in. And so I was fortunate to have such a situation for myself because I worked with Hani Mamasani on dynamic traffic assignment at a time when that was just emerging as a field. And I joined Purdue University as a faculty. And one of the things that I sought to do even then is I sought to go across the aisle in the sense of working with faculty from different disciplines, primarily because I felt the problems that needed to be addressed required expertise beyond my own knowledge. And just as an example, needing to interact with faculty related to provide knowledge on behavior, so you would have to go to work with, say, psychologists, people who work with technology. There are a bunch of engineering domains that would have interest in that space as well. So that became a natural direction for me to work in. And the other point that I wanted to share that I can think of in terms of an anecdote is when I was, these days, when you start out, as a new faculty, one of the things that you have opportunity for at the national level is to apply for what we call the NSF Career Award. And that is given to young faculty who have shown the promise or at least convinced the NSF reviewers that they have the ability to do good research and translate that into the ability to educate the future generations innovatively. And when I was writing that proposal, because at that time, there had been a 12-year period when nobody actually received a career award in transportation. And I remember my colleagues saying, you can do it, but it may not work out, so don't get disheartened. I said, let me try it, and I sent it to another division there, which is called Electronic and Communications, or Electrical and Communication Systems Division. And they actually reverted back to the Civil and Mechanical System Division and actually funded it. And the lesson I learned there is, unless we try, we won't know what we're capable of. And each and every one of you, being here, the fact that you're here implies that you have abilities that you can leverage quite a bit. And with hard work, you can achieve and reach the aspirations you seek to reach. So in that sense, all I have tried to do, even with my students, so that goes to the mentoring side, is I always try to, in some sense, push them to the best they can do. So as long as you can do the best you can, more often than not, you'll see that there is the ability to impact the field. So I don't know if I went long, Michael, but I just thought that would be a summary from this end to that end. So
well, thank you, Srini, for the sound advice and share with your personal experience. And I want to add to that is actually interdisciplinary and also persistence. And also keep on trying things is very important traits that to become a successful faculty.
Yeah,
and for,
just, Michael, that reminded me, the three things that I look at is integrity, perseverance, and hard work. So these are the three things. If you ask me what are the three things that have helped me, these are the three that I would consider the most valuable. Yeah. So thank you for bringing perseverance as well.
And also, for transportation, the interdisciplinary really shows in how transportation has evolved. Remarkably, some of the foundational work in transportation systems, particularly, are done by people not in transportation, and like physicists, economists. For example, some of the traffic models were done by physicists and applied mathematicians, and some of the models that Professor Peeta is using are proposed by economists. So it's the interdisciplinary nature for transportation is there very early on. Yeah. Okay, with that, I think it will open up to the question and answers. And so I want to remind our audience that for students, you can submit your questions and answers in the chat. And then for our other audience, and we'll have using the Q&A to ask your questions. So because the student audience, this is their class, so we'll give them the first the first chance to answer questions. So any of you have questions from our student audience? You can use the raise hand function if you want to ask a question. Well, so while the students are thinking about their questions, let me ask a question of the work that Srini, you proposed. Do I understand it correctly? This will be what I call a one-shot game, like it will be during a day and different times, then you route people to their destination, or this will be repeated day after day, so which I think is the first, right?
Yeah, it's the first one. It's the within day, but that within day happens from one day to the next. So when we say the expected sense, that was saying that in the expected sense, the gain, because if they keep losing, there's no incentive for them to participate.
Yeah, and I think for CEVs, probably these CEVs may not be be endowed to learn from their choice, because they are given these instructions and then they're going to pick the routes and so forth for their passengers. But for the mixed traffic, for the regular drivers, they can learn from what the system works and could be actually find ways to gain the system.
Exactly. And that's why we are able to leverage that here, that we couldn't leverage, say, for a human-driven vehicles. And the other thing that we benefit from is because once you code in your preferences, they're transparently available. And related to that, when we have a connected autonomous, so if you have an autonomous vehicle environment, the expectation is that people can gainfully spend their time, whether it is for work or for leisure. So they may not be as sensitive if the vehicle takes a route that sacrifices a little some time while gaining at other times. So.
And also, I was wondering, because when we do this sort of kind of a rolling horizon type of optimization, we're taking a kind of a myopic sort of view, right? Because the information is only up to a certain point. I was wondering if you can kind of benchmark that, compare with, having a system optimal assignment that you do for the whole day and solve the problem, and then see how much incentive or the routing, and compare with this, this kind of dynamic situation, and see what would be the difference between these two systems, and how kind of sort of bounded the performance.
Yes, that's a good point. We haven't done that in this paper, but that makes a lot of sense to see with incentives how close you can get to that. But in some ways, that also will be an idealized approach when we do the one, because it's making an underlying assumption that we have all the information, and here we wanted to bring in that realism. But nevertheless, it'll be good to see how much the incentive mechanism can allow us to get closer to that idealized state. Yeah.
Yeah. And do any of our students have questions? So if you don't have questions here, but I want to remind you that as your class requirement, you're asked to submit 3 questions afterwards in Canvas. So don't forget that. Yeah. So while we're, now I think I can open up to our outside audience. Actually, I have Jay signed up and have questions. So Jay, welcome to the seminar, and I want to see that Jay is a senior of Srini and got his degree from Texas with Professor Mamasani, and he was my professor. I took probably most of my courses from him. So just to give a background. So Jay, I'll let you ask the question instead of I'm reading your question. Are you still there, Jay?
Yeah, I'm here. Can you hear me?
Yes. Very well.
Good to see you both. Thanks for letting me speak, Michael, and great to see you, Srini. And I don't know if you saw a text that I said. I only saw.
I was going to mention that.
I only saw this morning that you're.
No, I had the text while I was preparing, so just so I said, great. I see Jay.
Yeah, yes. I mean, it's wonderful to hear you talk on this topic, especially this idea of considering our modeling, from an NV standpoint. I think only you and us at UCI have so far worked on applying NV topics really to transportation, and I think it is extremely relevant now that, as you said, the data is there, and so several preferences can be just revealed out there too, right? So from that standpoint, I think it's very nice to see that you're using it. Now, my question was, I have some thoughts on this, so I just wanted to hear you talk about it too, in terms of, if we have like an NV-based mechanism and we have some people paying and some people, receiving, the money. So it is almost like you're doing wealth distribution. If we can imagine sort of a political economic system, that comes out of human mobility, which is a big component of our transportation systems, right? So, I mean, if you had any comments on that, and I think on the regulation side, you already said, talked about how incentive compatibility will just kind of, prevent what's known as arbitrage. People lying to game the system, right? So you already commented on this. Just wanted to hear your thoughts on those things. Is it like a democratic idea or a Republican idea? That, that's one way of thinking. Go on.
No, that's an excellent point, Jay. In fact, I was thinking about that, and you're right. Because when you look at it, when we say that some people are, sacrificing their time, so in some sense, it means that they're gaining monetarily. And typically, people, if you look at value of time, the ones who have lower value of time tend to be people who are in the, a lower income group. So in some sense, there is this notion that maybe they are willing to sacrifice, which, especially if the value of time is not particularly significant for them, whereas there are people for whom the value of time can be very high. In general, if you look at it at the aggregate level, higher income individuals, because of their characteristics of the job, how much they value time, they're willing. So in some sense, some of this may over time reflect this ability to shift that, but do so in a way that is democratic. What that means is it is one where people are willingly participating without being penalized. So let me put this in a slightly different way. When we have tolls out there, tolls are penalties that people are supposed to pay. And in the process, the ones who can afford to pay are able to use it and benefit. And those that cannot, because of their constraints, the budget constraints that they have individually, will not. And so they will take and they incur larger costs and so on. Here seems to be a way where people willingly are trading in the market in such a way that there is more equity in that process.
Absolutely. If I could comment more, I don't know if there are other questions. Just a quick comment. Initially, when one of my earlier students, Roger Lorebetta, we had actually an ISTTT presentation at Chicago on signal control using NV-free techniques. So when Roger was doing his PhD, his initial question was, but isn't this like the rich people can travel better because they have money? So, very quickly, the answer to that is no, but that money is going to the poor people. So this is not like a quote unquote, a capitalist idea, but their money is being redistributed, which is more like a socialist idea. So it is somewhere in between.
It is based on willingness.
Yes.
It is something that also addresses equity. So that's a very good point. Jay, exactly thinking about it, I didn't put it in the content. We didn't even put that in the paper, but that was one of the things we actually had discussed. So this is a very important point. And one, given the value systems that, if you look at how values have been changing and being brought up in the transportation, equity and the need to, also benefit, say, underserved populations and so on, becomes particularly important. And some such approaches, and this is just scratching the surface, I'm sure there'll be other approaches that can be brought into play that in a democratic way will also enhance equity.
Yes, you and I should talk more on this. It's a very interesting point. Thank you for the talk, by the way. Really
Thank you, Jay. And
thanks, Michael.
Certainly, I think also, coming back to the sort of the congestion pricing, and if you collect congestion tolls and adding a redistribution system to address the inequity or equity issue, that you'll add an additional layer to the problem. But in your work, it's automatically addressed in the formulation.
Good point, Michael. Actually, that was done in Florida, for example, where they collected the tolls and they generated revenue, and then they used that to enhance the level of service of transit for people who couldn't afford that. So there are layers that you can add. You're right.
Yeah, and also for autonomous vehicles, it could be the future transit agencies will deploy fleets of autonomous vehicles, and therefore you have could have a different mechanism for kind of subsidizing the fleet or price incentives or disincentives for using some of the vehicles during peak hours, and so there opens up a lot of interesting scenarios that
exactly, because there's nothing that precludes us from getting more into this, because when we talk about using high occupancy vehicle modes, naturally that needs to be recognized because that benefits the environment and energy conservation, all of that. So
yeah, so there are many different possibilities. But, a policy, unless it's quantitative, then it's not a good policy. So you have to evaluate these things, and sometimes you have to go through sophisticated models to check, whether the policy really is what you intended it to be. Yeah.
Good point. Good point. And interestingly, we got inquiries from metropolitan planning organizations related to. We presented a much more abbreviated version, like TRB, of this work, and there was interest there. And I can understand, the point that you just made. It's exactly that, because we start out and say it's possible now to build, to have more democratic, equitable approaches. And then they see what works, what doesn't. There are also political constraints that come in. So in the end, there'll be different ones that work for different cities. But it gets them intrigued that we can now think of incentives in a different way to try to come up with solutions where we can also leverage emerging technology. So that would be particularly interesting.
Mm-hmm.
Yeah, and another interesting aspect would be non-monetary incentives, particularly for our students' generation, for the millennials, and the sense of sustainability and the recognition of this issue in equity is, I think, I would see a more keen and stronger, and probably non-monetary incentives can also go a long way. That would be another interesting problem to look into.
So Michael, you're thinking way ahead, because there's a companion PhD effort going on with another student. Her name is Rupa Anne, and she's doing exactly that, where we are looking at incentives. So she's actually building an app where we look at incentives which are monetary and non-monetary as well. And some of them are to leverage this, what social media allows us to do, especially the things related to reinforcement, where where they have friendly competitions. So there are things where you provide incentives, like there are other studies that have already done that. They have raffle tickets to games and things like that. So there are different ways by which you can do that. So a companion PhD to this is actually doing that part of it, and we are actually coming up with formal methods to be able to do that. And the idea is that at some point, the two of these are going to be merged.
Yep. Okay. Any last minute questions from the audience? Well, if not, we want to thank Professor Peeta again and for his talk, and give a round of applause.
Thank you.
Yeah. And with that, I think we'll conclude our seminar today. And so thank you, Srini, and good to see you.